if a carbon can continuously form bonds to other carbons, that there's no reason to suspect that it couldn't come around and kind of bond to itself. Now, the smallest possible cyclic alkane we can have is the three-membered cyclic alkane, as I'm drawing here. Okay, and the way that we name this is by looking at the number of carbons that are in the ring. In this case, there's 3. What's the prefix for 3? Tri. Well, it can be tri, but pro. Okay, so this is a propane system. This is cyclopropane. Okay. Okay, what we call this? Okay, so 4 carbons based on butane, but it's a cyclic system, so it's cyclobutane. Now, from here on in, I'm going to start getting a little bit lazy. Instead of drawing all those H's and C's, I'm going to just draw the line drawings. What do we have here?
Cyclopentane.
Cyclopentane, and then no, it's not hexane. It's cyclohexane. The reason why I'm really emphasizing this is because I could draw cyclopropane as the much more familiar shapes of triangles and squares. As a matter of fact, I remember when I was taking general chemistry, I must have missed the class. They talked about cyclic compounds because when they asked the question, what is this, when they put the triangle there, I wrote triangle. And I thought it was like one of those trick questions that the teacher's going to give you a point. No, it wasn't. I got it wrong. Okay. Okay. So those are some of the cyclic compounds that can possibly exist. Now, with that being said, let's see here. What I'd like to talk about next is the reactions of alkanes. Okay. Now, alkanes are kind of funny when it comes to reactivity. You see, an alkane is composed of carbon-carbon bonds and carbon-hydrogen bonds, which are among some of the stronger bonds that are known. So how reactive do you expect them to be? If their bonds are very strong, there would be a huge activation barrier that needs to be overcome in order for it to do anything. And for that reason, the reactions of alkanes are quite limited, especially in the case of sophomore organic chemistry, because without the help of some very, very sophisticated techniques, alkanes won't do anything at all, except for 2 things, of course. A hydrocarbon in the presence of oxygen, with the help of a spark, will produce carbon dioxide and water. What kind of reaction is this? Combustion. Folks, there's chemicals out there that if you just look at them cross-eyed, they would just start reacting. They're so reactive. But an alkane, if you were to take methane or ethane or propane, stick them in a bottle, and just let them sit for 1,000,000 years and open those bottles up, you'd still have that compound there. It's not going to do much. Okay? But in order to get it to do anything, there needs to be a catalyst, right? Okay, you can't have a fire without a spark, right? Okay, either that or an immense amount of heat. Either way, what you wind up doing is generating enough energy that you can cleave at least one of the bonds. And once you break one of those bonds, then it's a chain reaction after that. Because now once you break a very, very stable bond, the intermediate that's produced as a result is super reactive. So basically, the molecule begins cannibalizing itself and all the other molecules around it until it's fully oxidized, completely consumed, forming carbon dioxide and water. Now the other reaction, and I want to actually show this with a real example, is the reaction of an alkane with chlorine let me draw it out. To form an alkyl halide. Now, this reaction will not work without the presence of those two letters, H and nu, which is an abbreviation we use in organic chemistry to symbolize light, usually UV light. UV light is capable of initiating some crazy reactions. I mean, I don't have to tell you that. We've all seen those reactions take place in our skin if we spent too much time out in the sun, right? Okay. It can lead to mutations. It can cause DNA to bind to DNA in places that it's not supposed to be binding. Okay. It'll make DNA get stuck to itself to the point that it can't divide or divides too much. There's the UV light that is used to energize all those bad reactions in your body can be harvested, though, to react with alkanes. And we're not going to get into the mechanism of this. However, the mechanism is in the textbook. The reason why I'm not getting into the mechanism is because of all the reactions that we're going to learn about, this is the only one that goes by this mechanism, and I'd rather you just focus on the mechanisms of the others. All right. So are there any questions about alkanes at this point? Everybody feels pretty comfortable with them? All right. Let's move on to Chapter 3. Okay. Up until now, we've been looking at carbons that are mostly involved in just single bonds. Those carbons are what we call saturated. In other words, each carbon is bound to as many hydrogens as it can possibly be bound to. For example, we looked at this just a little while ago. That's ethane, right? Every carbon has 4 bonds, and every carbon is bound to either hydrogen or carbon with a single bond. There are no double bonds present, no triple bonds present. We say that this is saturated. Now, if I were to draw a double bond between the 2 carbon atoms, just as it is, I'd be breaking some rules, right? Each bond would have, or each carbon would have 5 bonds, right? So if I wanted to form a double bond between those 2 carbons, what do I need to sacrifice? I need to sacrifice 2 hydrogens. Okay, and this is an alkene. Okay, which is decidedly not saturated. If you look at the alkene, you'll see that each one of the carbons could potentially be bound to another hydrogen if we got rid of the double bond. Okay, so each carbon is not bound to as many hydrogens as it possibly can be. And in an alkyne, we have a triple bond. What must I lose in this case? 2 more hydrogens have to go by the wayside. Okay, and of course these have their own names. We have ethane over here, and we have ethylene or ethene. Let's use ethene here. That's the IUPAC name. And over here we have ethyne. But you will never, ever hear anybody call this ethyne. It's acetylene. Now, if we look at the saturated versus the non-saturated compounds up here, we could argue that the alkene and alkyne have differing levels of unsaturation. Because in the alkene we have 1 fewer set of hydrogens, we could say that there is 1 degree of unsaturation. The alkyne has lost 2 sets of hydrogens, so that would be 2 degrees of unsaturation. Any questions there? Now, does anybody remember what the hybridization was for an alkane? Okay, let me word this differently. When we look at the electron configuration of carbon, does it necessarily match up with the bonding that we see it undergoing? No, it doesn't. How did we rationalize 4 bonds in a tetrahedral arrangement of substituents? Hybridization of orbitals. And when we did that, what orbitals did we take? We took 1 s orbital and 3 p orbitals and put them together to get sp3 orbitals. Okay, so the alkane is sp3 hybridized. All right. How about the alkene? Do you think the alkene is going to be sp3 hybridized also? Remember, the sp3 hybridization was what was accounting for carbon being bound to 4 different groups. Is carbon bound to 4 different groups? No, it still has 4 bonds, but it's not bound to 4 different groups. Okay, it's actually only bound to 3 different groups. And I'll tell you right now that it is sp2 hybridized. And the ethyne, it's only bound to 2 things, so it's sp hybridized. So let's make some sense of this. When I say something is sp3 hybridized, like I said earlier, I am taking one s orbital and 3 p orbitals to give 4 sp3 hybridized orbitals. Okay, and that s orbital and those 3 p orbitals, they all came from the outer shell, the valence shell of carbon. Well, let's say we do this sp2 hybridization. If I take that s orbital, but this time only hybridize it with 2 p orbitals. What I wind up with, I'm sorry, this is p in the x-axis and on the y-axis. How many of these sp2 hybridized orbitals should I wind up with? 3, thank you. What happened to that other p orbital? Did it just go away? It just stayed a p orbital. So we wind up with an extra p orbital left over. Okay, and if the first 2 p orbitals we used were x and y, this would be the z p orbital. Okay, and then in an alkyne, we're taking an s orbital and a p orbital. Okay, in this case, I'm just going to show p on the x-axis. That should give me an sp orbital, but how many? 2. But I can't forget what else is there. What else is going to be there?
Y and Z p orbitals.
Right, the y and z p orbitals. So we'll show 2 of those, p, y, and z. Okay, so the most fundamental difference between an alkane, an alkene, and an alkyne is the number of available p orbitals that can be used. And I'm going to show you how that kind of comes into play here. The other difference, and you might think that I just started getting lazy and drawing my hybridized orbitals there, but you did see that the sp3 is much more elongated than the sp2 or the sp. Did everybody notice that? That was on purpose. Okay. Can anybody think of why it would be that the sp3 hybridized orbital should be more extended and longer than the sp hybridized orbital? What's that? There's more p orbitals. Yes. No loss. No bonds yet. Think about the. Yep. Sorry. Go ahead.
To get away from the other electrons, to get further away.
No. This is just a region of where they can be. Okay. There's no electron there right this second. This is due to the mathematical addition. I'm sorry. Do you have one? Oh. This is due to the mathematical addition, an algebraic addition of the s orbital and the p orbitals. Think about what the p orbitals look like. Dumbbells, right? What does the s orbital look like? Circle. Okay. Would you all agree that as we remove p character, in other words, the p elements of the orbital, that S must then take up a larger percentage of the composition?
Yes.
Is that unanimous? Okay. If you look at the alkyne, it's 50-50, S and P put together. If you look at the ethane, it's one S, but there's three P's kind of overwhelming it. So when you have an sp orbital, it's going to be more spherical. It's going to look more like the s orbital than in the case of the sp3 or the sp2. This turns out to be very important because with this orbital being so much smaller on an sp hybridized carbon, it has a huge impact on how a negatively charged pair of electrons can stabilize themselves due to being closer to the nucleus. And we'll talk about that a little bit further on down the road. But do note that the sp3 hybridized orbital is going to be larger. Now, this also says something else. If the sp3 hybridized orbital is longer, more elongated than the sp2 hybridized orbital, which one of these three is going to have the longest bond length?
The first one.
Do we all agree? Right. The longer the orbitals, the bigger the orbitals, the further apart those carbon atoms can be and still have an effective bond. What about the alkene?
Which one?
Well, we know that the sp2 hybridized orbitals are less elongated. So those carbons need to get just a little bit closer together in order to have a meaningful interaction. And then in the case of the alkyne, they need to be even closer. Let's take a minute to look at the bonding here. If I were to look at the bonds on an alkane, what I would get is something that looks like this. It would be the overlap of the sp3 hybridized orbital overlapping with the s orbital of a hydrogen. Okay, so this is the equivalent of a CH bond when the carbon is sp3 hybridized. Now, I could go around drawing the other three hydrogens in, okay? But I'm not going to do that right now. Let me draw this out as a molecule. Let's look at ethane. Okay, in ethane, I'm going to draw the hydrogens. But this time I'm going to emphasize that carbon-carbon bond by drawing it as the overlap of two sp3 hybridized orbitals. Okay, and there are two electrons in here that are sharing these two orbitals, making it a bond. Okay, remember that the carbon has a tetrahedral geometry to it. Now again, I said this was ethane. Notice that the two orbitals, how are they lined up with one another? Are they overlapping head to head or side to side? Head to head. Whenever you have a head to head overlap, we call that a sigma bond. Okay, and usually you'll see that abbreviated as the Greek letter sigma. Now, in the case of ethene, things are a little different. I'm going to draw the carbons out here. And we're drawing the hydrogens. So I'm going to bring them a little bit closer together because the carbon-carbon bond between an alkene should be shorter than that of an alkane. Okay, I'm going to draw my Sp2 hybridized orbitals. Now I want you to think about this. As I have this drawn right here with just a single bond, how do you imagine the geometry is for each one of those carbons? Is it still tetrahedral? What's the point of being tetrahedral? Why bother? Why not be square planar? What does tetrahedral get you? Right, you're maximizing the distance between the electrons. Remember, I told you folks, there are 3 principles that govern everything here. Opposites are going to attract, electrons are going to repel from one another. So how can you get 3 groups as far away from each other when they're attached to a sphere? It has to be flat. They have to be coplanar. And they have to be 120 degrees to one another. So whereas the ethane was tetrahedral, the ethene is going to be planar. And of course, it still has electrons that it's sharing. Now, please remember that each one of these bonds here is, in fact, a bond using Sp2 hybridized orbitals. Whereas each of the bonds up here were all created with Sp hybridized orbitals, or sorry, Sp3 hybridized orbitals. I just decided to show the carbon-carbon bond to emphasize that point. Is this a sigma bond? Are the 2 bonds head-on? Or 2 orbitals are head-on, overlapping? So yes, this is still a sigma bond. But if we go up a little bit and look at that Sp2 hybridized ethene, we know that there's a leftover p orbital, isn't there? We can't just forget about that. That p orbital is still there. Okay. Now these drawings aren't to scale. But each one of these p orbitals is bringing an electron to the dance. All right, these electrons are going to want to get together, pair up. I know that we want electrons to repel, but unpaired electrons are even more unhappy. So what that does is eventually gives us some overlap between those p orbitals. Now, if I have 2 p orbitals overlapping with one another, is that a sigma bond? Why not? Okay, they're coming in end on. We would want them to come in head to head for a sigma bond. Instead, we have what's called a pi bond. Now, I know it looks like I've drawn 3 bonds total here, but there's 2 bonds. The pi bond is actually existing on the top surface and the bottom surface of the alkene. Now, there are some very, very important implications from this. First off, those electrons that are part of the pi bond, they're kind of out in the open now, aren't they? The electrons that are part of a sigma bond are kind of shielded. They're in between those two carbon atoms. They can't do a whole heck of a lot, and even if something reactive wants to get in there, it's going to have to be really reactive to get past those carbons and do something with those electrons. But the pi bond's different. The electrons are kind of out there, they're not protected. Which do you think would be more reactive? An alkene or an alkane? An alkene. Okay? The alkene is actually primed for attack. Now, that being said, if you look at the carbon-carbon bond of an alkane and the carbon-carbon bond of an alkene, and I'm not saying sigma or pi, which one's going to take more energy to break? The double bond or a single bond? The double bond is going to take more energy to break. Why? Well, it's a stronger bond. That's right. It's a shorter bond. And there's a second bond, right? You have to break the pi bond first and then apply enough energy to break the sigma bond. But the thing to remember here is that one mistake that we sometimes make is to look at the alkene and say, oh, but the pi bond is weaker than the sigma bond, so it's easier to break. The pi bond is easier to break than the sigma bond, but overall, to break up the two carbon atoms, it takes more energy for ethene than it would take for ethane. And to extend this further, let's take two carbons, draw them close together like this, because for an alkyne, they need to be even closer together. Oh, this is ugly. Then we're going to give them a little bit more room. Okay, so what kind of bond is holding together those two carbon atoms?
Triple.
Okay, it's a triple bond, but as I've drawn it right now, there's a single bond. What kind of bond is that? It's a sigma bond, right? Okay, the two orbitals are coming in head on. Now, if I look up at the hybridization for an alkyne, I see that I make two Sp hybridized orbitals and two p orbitals are left over. So where do those p orbitals live? Orthogonal to the previous set of p orbitals. So this is the first set. Okay, and here's the second set. And forgive my attempts at 3D sketches here. Okay, they are orthogonal. If you were to look at this as a Newman projection, if I put the carbon, here's the front carbon, here's the back carbon. The H's you wouldn't even be able to see because they'd be right in that line. and the one axis would have one set of p orbitals, and the other axis would have the other set of p orbitals. So you can kind of imagine as the alkyne as being kind of a rod that's been kind of enclosed with an electron cloud. By the way, what is the geometry now of an alkyne?
Linear.
It's going to be linear. Okay, by virtue of that being the only way to get the two groups as far away from each other as possible. All right, so how are we feeling about this stuff? Are there any questions about it? I know that I've definitely opened up a few cans of worms here, so somebody must have a question.
What's the bond angle on ethane? What's the bond angle on
On
that?
ethene,
Yes, sir.
it would be, we would generalize it as being approximately 120 degrees because three groups spaced out evenly on one plane is going to be, each group's going to be separated by 120 degrees. But because carbon is going to have a different repulsion than the two hydrogens, it's not going to be exactly 120. But it's definitely going to be larger than the 109.5 for an alkane. All right, so let's go take our 10-minute break now since most of you are glazed over pretty good. And we'll